In the last video, I talked about exponential functions and how they grow very quickly. Let's take a look at an actual example here. Let's use the example y equals 2 to the x. In this case, I'm just going to pick some x and y values and calculate some points and plot some points and see where this is at. Now, normally when we graph, we want to see some negative values, some positive values, usually pick some values like 0 that are easy to calculate. I'm going to throw negative 10 in there just to see what's happening all the way over there. And then negative 2, negative 1, 0, 1, 2, 3. And I'm going to throw in positive 10 to see where we're at. Now to find the y value, you could just grab your calculator and type in 2 to the negative 10. If you did that, your calculator would give you a number close to 0.001. But I'd like you to think about this for a second. In algebra, you learned about dealing with negative exponents. Likely you were told if there's a negative exponent, you need to put it on the other side of the fraction. So in this case, we put 2 to the negative second on the bottom, make it positive. 2 squared is 4. That's equal to 0.25. Think about 2 to the negative first. Similar, we get 1 over 2 to the first, which is just 1/2, or 0.5. Here we get 2 to the 0, which is 1. 2 to the first, which is 2. 2 squared is 4. 2 cubed is 8. And 2 to the 10th, we get 1024, 1024. And so you could see these numbers grow very quickly. So we start all the way over here at negative 10, which is basically at 0. And then even at negative 2, it's still really small. It's at 0.25. Zoom in a little bit here. And then at negative 1, we're at negative 1/2. 2 to the 0, we're at 1. 2 to the first, we're at 2. 2 to the second is 4. 2 to the third is 8. And then I'm off the charts. I can't even draw 2 to the 10th. But if I did, it'd be 1024. It'd be about 10 times higher than this distance here. So you can imagine that's clear above your screen. So we see exponential functions start out really small, really close to 0. And then they just shoot up really, really quickly. It looks something like this. Let's take a look at another example here for y equals 1/2 to the x. So y equals 1/2 to the x. I'm going to do it in green here. I get the x and the y. I'm going to choose similar points here. Negative 10, negative 3, negative 2, negative 1, 0, 1, 2, 3. Actually, let me do 10 instead of 3. All right, so now we get a little bit more challenging calculations here. 1/2 to the negative 10th power. I'm going to do that down here. 1/2 to the negative 10th power. I don't know what your inclination is to do here. I think some people would take 1 to the negative 10th and distribute this. 2 to the negative 10th. And then using your negative exponent rules, the 1 to the negative 10th gets moved to the other side of the fraction, becomes positive. The 2 to the negative 10th goes to the other side of the fraction, in this case the numerator, and also becomes positive. 2 to the 10th then is 1024. 1 to the 10th is just 1. 1024 divided by 1 is just 1024. This number looks familiar, doesn't it? We had it right over here. Kind of interesting. Similar thing's going to happen with 1/2 to the negative 3rd. We're going to end up getting 1 over 2 to the 3rd, which gives me 1/8. I'm sorry, that's not correct. Going to be 1 over 2 to the negative third, which equals 2 to the third, which equals 8. Similarly, here we have 1/2 to the negative second, which gives me 1 over 2 to the negative second. I've been dropping that 1 because 1 to any power ends up being just 1. That gives me 2 to the second, which is 4. Similarly, we get 1/2 to the negative 1 is 2. Anything to the 0 power is 1. That's going to become pretty important. 1/2 to the first is just 1/2. 1/2 to the second is, again, you can see 1 squared over 2 squared, which just gives me 1/4, 0.025. And 1/2 to the 10th is just going to be 1 over 1024, which again is close to 0.001. Next, I'm going to graph these. -10, again, I can't graph it. It's way off the graph. But when I get to -3, that's at 8. -2, that's at 4. -1's at 2. -1. Sorry. At x equals 0, y is 1. When x is 1, it's 1/2. When x is 2, I'm at 1/4. When x is 10, it's basically 0, just about 0. And again, we get a similar curve, but this time, instead of starting really slowly and then shooting up really quickly, this one starts quickly, drops off quickly, and then ends up close to 0. Now let's compare these two graphs. You'll notice they look similar. The only difference is they're a reflection across the y-axis or a reflection in the y-axis. Let's take a look at why this is. Up here we had y equals 2 to the x. Let's compare that to y equals 2 to the negative x. If you remember from our transformation section that when I have a negative sign inside my function, it's a reflection across the y-axis. So this negative is going to make a reflection of y equals 2 to the x across the y-axis. Now let's take a little closer look at 2 to the negative x. Lost it there. Here we go. Two to the negative x. Remember the rule I showed you a little bit earlier? Negative exponents go to the denominator. And then, since 1 to any power is 1, we can rewrite that as 1/2 to the x power, which is exactly what we had here. So there's a connection here between 2 to the x, 2 to the negative x, and 1/2 to the x. That is helpful to see. Let's take a quicker look at a few questions. Why does a have to be greater than 0? Well, let's think about this. If a is greater than 0, we see these two types of graphs. But if a equals 0, y equals 0 to the x, that's just 0 times itself a bunch of times. That doesn't work so well, does it? All right, well, what if a is a negative number, like -2? y equals -2 to the x. This is just going to cause all kinds of trouble. If x is an even number, -2 to an even power will be positive, but if x is odd, it will be negative. And then we get decimals, and we don't even want to go there. So the short answer here is, why does a greater than 0? Why does a have to be greater than 0? Short answer is, so we have a smooth curve. And really, it's going to be an exponential growth. If we don't, it won't be exponential growth. And that's the same way here. If you think about a equaling 1, y equals 1 to the x. Well, that's just going to end up being 1 times 1 times 1 times 1 times 1, depending on what x is. And so really, we're interested in exponential growth, even though in some cases we get exponential decay. If you take a look here at these graphs, you can see we have this green one, 0.4, 0.25, 0.7 to the x. You notice these all follow what we call exponential decay. Over here, you see what we call exponential growth. So the question is, why are these all exponential growth and these all exponential decay? Take a look at it a second. You probably noticed that the numbers on the left here are all between 0 and 1. So when a is greater than 0 and a is less than 1, we get exponential decay. However, if a is greater than 1, we get exponential growth. So, to summarize this video, I've covered a lot of ground, but we really just looked at a couple examples, plugged in values, worked with negative exponents, which is a bit challenging, but we see no matter what, when we have a greater than 0 and not equal to 1, we get a curve that has a horizontal asymptote. That's a new word. This horizontal line right here that it gets closer and closer to and then shoots off if it's exponential growth. If it's exponential decay, it still has a horizontal asymptote, but this time it starts high and drops off very quickly towards that horizontal asymptote. We see that when a is between 0 and 1, we have an exponential decay, but when a is greater than 1, we have an exponential growth.